Hey guys, this is Srini and thanks for watching this video. And while you're here, please go ahead and hit the subscribe button. Now, let's get into today's topic, which is working with 3D and multi-dimensional images in Python. And I'm recording this because quite a few of you have requested about this specific topic, especially the comment section of Gaussian filters, denoising filters. And I see quite a few asked about, okay, what about multiple images and what about 3D images and so on. So this is a quick video talking about how do you load them, how do you load these multi-dimensional images, and how do you work with them. And not every library that's available out there is applicable to 3D space. In fact, very few of these modules are written for 3D space. It's unfortunate, but we can always work with 3D images and apply these one 2D slice at a time. Okay, now let's jump into the code and get it done. Okay, so let's jump in. Now, before looking at the code, first of all, let's see what we are talking about. So when I say 3D images, here is an example. Okay, so it's a Z stack. For those of you outside US, this is a Z stack, right? When I say a Z stack or a Z stack. So here is like image number 1, image number 2, 3, 4, 5, and so on. And then this is like, as you can tell, these are like some sort of a spherical things. So there you go. Okay. So now you would like to apply, I don't know, histogram equalization or something to these stack. And how do you actually handle this, right? You have to load this. Again, the answer is one slice at a time, most of the time. Okay. And you may also have time series. It's like a video. So I have one of these images right here. You see, this is at time 1, time 2, time 3, time 4, time 5, and so on. Yeah, things are changing over time. How do you load this and measure, I don't know, the area here or do some sort of a processing to these images? Now, these are simple cases. Now, in real scientific images, there may be even more complicated. So let me open an image in ZenLight. This is by Zeiss, and again, this is an amazing piece of free software. Of course, you can unlock advanced features if you pay, but you can work with multidimensional images. There are a whole bunch of image processing functions here. So if you really want this, go ahead and Google search for ZEN or ZEN Light, L-I-T-E. Okay, this is great software. Anyway, this image is again a scientific image, obviously noisy for sure reasons I don't want to get into. This is biological imaging. So biologists, you probably know what we are dealing with here. And you see, this is I'm going through Z. I'm going through depth or Z, if you want to call this. And also, this is also a time series. Yeah, I'm going through the time. So for a given Z, I have the entire time series. Or for a given time, I have the entire Z. And this image is not just one image. This is actually 2 channels. So the green channel and the red channel, right? I can turn each of these channels on and off. So this is as complex as it can get. Well, it can get even more complex because if you just think of this having multi-scene, okay, this is scene 1. Now the same thing you repeat with scene 2, scene 3, scene 4, right? So things can get a bit more complicated. So now that we have a good background in terms of what we're talking about, the 3D and time series, let's just jump in and see a couple of ways to handle this, okay? Again, I'm going to show using scikit-image and how we go through, how we load the image, how we look at each plane by plane. I don't know if you find this to be too basic for you, too advanced. I mean, it depends upon your skill set, so please gauge it accordingly, okay? I don't want to bore those of you who already know a lot of basics in terms of NumPy arrays and everything. You may learn something here. Okay, so let's go ahead and import our standard libraries, which is for plotting, right, and NumPy. And from scikit-image, I'm going to import some of the useful libraries. You'll see that in a minute. Okay. First of all, scikit-image, I like to work with scikit-image when I'm dealing with these type of multi-dimensional images because scikit-image's io.imread actually includes, for example, if you're reading Tiff file, it uses a library called Tiff file, T-I-F-F-F-I-L-E in the backend. And that is designed to actually work with multi-dimensional TIFFs. Okay, so scikit-image is pretty good to read these type of images. So let's go ahead and load the 3D image we just looked at. And if you look at the dimensions right there, it says 129 by 308 by 461. Normally, if you just load one image, you're probably used to seeing, okay, 512 by 512 by 3. Because this is a color image, you have 3 channels. If it's a gray image, 512 by 512, right? So here, this is a gray image. of size 308 by 461. If I open this image again, this image is 461 by 308. You see, like 308 in height and 461 in width. Okay, and each image is a gray image, and I have 129 of them, right? So that's the depth here, 129. That's exactly what we're talking about here. We have 129 images. So you see how the dimension shows up in the Z dimension is the first one here. So 129 in depth, 308 in height, and 461 in width. Okay, this is how you can interpret this. So that means all I need to do right now is go from all the way from image 1 to image 129. Let's open this, image 1 to image 129. So this is 0th image, first image, second, 3, 4, 5, 6, 7. So load each of this, process, save. That's pretty much it. Okay. Now for visualization, let's go ahead and do something. I'm converting this image into UByte, which it is already, I believe. I don't know what I think I was doing some experimentation in terms of converting this into applying a filter, but that ignore. Oh, sorry. There's a reason why I'm doing this here. I forgot about this data set. If you look up here, it says unsigned integer 16. So the values are going from 0 all the way to 2 to the power of 16. Okay, but let's convert that to UByte, which means the values go from 0 to 255. Okay, sorry about the confusion. I should have been a bit better prepared about my own data. So now you see the array is of size. Again, this is optional because some libraries, they kind of work on only 8-bit images. Then it throws some error. So in this case, I'm not losing much of any information by converting. So I'm converting this. Okay, so I converted the entire array into unsigned integer 8. So my values go from 0 to 2 to the power of 8, which is 256 or 255 in this case, 0 to 255. Okay. So let's write a function for showing a plane. Again, this is very basic plotting. So all I'm trying to do is basically plot. So we can look at each of these planes. Again, this video is not about plotting this, so let's not worry too much about this. But all I'm trying to do is looking at the plane xy, xy, xz, and yz, right? These 3 planes. So I'm looking at this volume from top down, from the side, and from this side. Okay, that's exactly what we are doing. And as you can see from the top, it's exactly what you. Sorry, I'm looking at the 50% of this, like somewhere in the middle, like this slice. Okay, so this is from the top, and from the side you're seeing the cross section, and this is the other side of the cross section from this direction. Okay, so that's just quick visualization there. And also let's go ahead and look at each of these slices. Okay, the first few of these, so you get an idea of what we're talking about, right? This is the 0th, first, second, third, fourth, fifth, and so on. This is basically, we are just I'm just showing you a couple of ways to look at this. Right there, 0, 1, 2, 3, 4, and we are plotting all the way up to here. That's pretty much it. So in case you don't have, I'm using ImageJ to kind of go through these images, but in case you don't have a way of visualizing these images, of course you can plot and look at them here. Okay, so far so good. And there are some libraries like Napari, for example, a couple other libraries that allow you to visualize images, the 3D images from, in Python. I tried to install a couple of those, but it requires like some, it comes with so many dependencies. I kind of gave up after a while. Okay, so this is fine. I'm looking at cross section and I have ImageJ. I'm good. Okay, now some modules in scikit-image, for example, if you do Gaussian, okay, you can apply that to this these images, even though this is 129 by 308 by 461. But if you try to apply this to the same set of images but in color, then that would be 129, 308, 461 by 3, then it throws some sort of an error, right? But just to show you that this can actually do, let's go ahead and I'm importing Gaussian from scikit-image, and I'm just applying that onto our 3D image. It should be very quick actually right there. And you see the Gaussian smoothed is 129, 308, 461, same dimensions. Scikit-image actually changes the values from integers to floating point, obviously to make sure you don't lose anything from rounding errors. So it's right there, but we can still go ahead and plot it. So let's go ahead and plot our before and after. So here is the image before, the original image. I picked just one slice of our volume, image number 9. You can change it, it's up to you. And here is the before and after. You see, the nicely Gaussian smooth. There is a lot of noise right there. So it is working. It is actually working. If I go to 50, for example, and go ahead and plot it, you see it's actually smoothing each of these images. I should actually do the same. Again, this is the issue of writing code where you have to change things at multiple places. But anyway, so this is the before and this is the after image. Okay, so it's actually doing what it is supposed to do, but that's just Gaussian. There are many other things that you may want to do. So how do you do that? Again, like I said, individual slice at a time. So in this case, I'm creating like an empty list. Here is the deal. Let's segment our image. Just binarize it. Okay, very simple. You can use Otsu for that, to find the automatic thresholding, but let's just go ahead and set a threshold of 50. Every pixel above 50, I'm going to assign a white pixel or true. Everything below 50 is black, right? So that's the task here. So what I'm trying to do is create an empty list called binary image to capture, whatever we are going to segment this entire volume. And for image in our range, sk3d image.shape0, which is basically saying that for image in 0 to 129, do the following. What is the following? Well, first of all, my temporary image is image, which means the first time in the for loop, the image is looking at the 0th image, the next one, the first image, next one, second, third, fourth, fifth. How long is it going to do that until the range is reached, which is until 129? That's very simple. Again, I told you, some of you may find this to be basic, but it is what it is. Okay. Once you have the temporary image there, now I'm going to set a threshold of 50, and then I'm going to define another temporary image called binary, where all the pixels above the threshold value are true and below that are false. So I'm just binarizing this image, and I'm going to append that to my binary image that I just captured. So at the end of this operation, I should have a list of 129 NumPy arrays, all processed, each corresponding to individual image, and I'm converting that into 8-bit. So when I save it, I can open it in any program. So let's go ahead and run these lines again. Okay. So we are just binarizing it. So now if you look at your binary underscore image right there, it's a list of 129 NumPy arrays. So let's convert that into a NumPy array, the entire thing. So np.array, I'm pretty sure you know how to do that. And now let's actually run this display function. Remember, there is a reason why we put this in a function, the plotting, because we want to do multiple plots later on. Okay, so instead of the original image, now let's actually look at the processed image, each slice. Okay, so if I go back to the plots, here is the processed, here is the original. You see, this is thresholded, original, thresholded, original, thresholded, original. Okay, so that's it. Here we just segmented it. Obviously, you can add many more steps of your processing, Gaussian smoothing, median filtering, whatever you would like to do, watershed if you really would like to do that. All of that can go in here. And let's go ahead and just look at one of the images. Okay, so there you go. So that's the segmented image. Now if you want to save it, go ahead and use io.imsave, and it does save it as a 3D image. So let's go ahead and open that processed image right there. Let's open it in image.j. And there you go. You see? So this is our image. And if you look at the histogram of this should be all binary, right? Either 0 pixels or pixels with a value of 255. So this is how you can kind of binarize your image, a 3D volume. Now, I just showed you an example of 3D data, but when it comes to Tiff files, there is no difference between 3D and time series, because if I load this other image, the time series image, now if you look at sk.time series, it says there are 10 images, each image 289 by 400. So from a dimensions point of view, it's still the first one right here, right? So I'll get to the bit complex situation in a second. Now, I am going to share this code. That's why I added these lines so you know exactly what TIFF file is. So if you use TIFF file to do this, this is the engine behind scikit-image, okay, when you're dealing with TIFF files. So if I load these, then you'll see that it's pretty much the same thing. TIFF 3D image is 129 images, 308 by 461. The values go from 3120, for example. Where is our, let's go ahead and read this image again. Sorry. Let's go ahead and read this image again, and it should be identical. Okay. SK image 3D 3120, 4222, 4222, yeah, 3855, exactly the same. So this proves that, okay, it's images are not changing when you're using scikit-image or TIFF file. Now, when it comes to complex images like this, like the one I just showed you here, now regular TIFF files cannot handle this, so you have to work with either something called OME TIFF, Open Microscopy Environment TIFF files. Again, in ImageJ, you can save any, most images into this format, or you can work with proprietary images. .czi is Zeiss's extension. Carl Zeiss's extension, but if you have a different microscope or different imaging device, not just a microscope, you may have your own proprietary images. And most of these companies, they provide libraries for us to read these images. Okay, and then we can process it. Once you read it, it becomes a NumPy array, and you can process it any way you want. Okay, and especially Zeiss is very good at being open about giving these the access to these libraries, and they work with open source community to make sure these files are readable in Python, especially. Okay, so let's clean the slate, and let's go ahead and start from scratch. This is my file name. So let's go ahead and import a library called CZI file. Okay, so Google search for CZI file. It's basically as simple as pip install CZI file. I did not encounter any issue. And if you have other libraries like other extensions, the process would be the same. You find what library enables you to read those images, and once you read the image, you'll see up here in a second, it's just a NumPy array. In this case, it's got too many things going on. Why? What's up? What's going on with this size, right? Well, first of all, this image is 587 by 587, okay, in size. If you go to the info, it tells you everything about it. The image dimensions are 587 by 587, okay? It's an 8-bit image, and it has 23 slices in the Z stack, and it has 11 frames. Now let's go back. It has 23 slices, and it has 11 frames, and it has 2 channels, right? We saw that. 2 channels, one for green, one for red. It has 2 channels. So an image is not just represented by just XYZ anymore. Now you have much more information. Okay, and what is the first one? The first one is for the scenes. Like I said, you can have multiple scenes. So, but even though this is a complex thing, it's a bunch of numbers in a NumPy array, and we read it. So if you look at the shape, again, we just looked at it. These are the numbers, and it represents to scene, time series, the channel, and all that. So if you really would like to just extract a specific channel, specific image, which is what I'm trying to do here, I'm looking at the 0th scene, time series 5, 0th channel, 11th Z, and then all pixels in X and Y, and then this is a black and white or a grayscale image, so 0 here. And I'm doing exactly the same for the next one, except I'm looking at channel number 1. So basically I'm looking at green and red image for 5th time point and 11th Z. That's all this is. So I'm just doing a quick demo of how to extract these. So there you go. So now we have these 2 images, and we just need to plot them. So let's go ahead and plot these 2. So you can actually see that we have exactly the same, yeah, except once it's only the green and it's only the red. So now you can actually process it any way you want. Now you can put your for loop, except in this case, instead of just one for loop going through each slice, you probably have 2 nested for loops, one for the Z and one for the time, or the other way around. It's up to you. Okay, and then process it and put them back together. Okay, so this entire tutorial obviously is turned out to be just a tutorial on how to use for loops to go through this NumPy array, but this is it. I mean, if you really would like to apply a lot of filters onto your images slice by slice, this is how you do it. Now, There are 3D operations that you can actually do. I believe non-local means filter, for example. You can do that in 3D, but it takes forever if you have a normal poor man's computers, right? But unfortunately, the very little few libraries can actually handle 3D in its native 3D state, like applying a 3D kernel and not just 2D slice by slice. So one day I'll again find time to make a video after identifying some of the useful 3D libraries. But stay tuned, keep watching, please subscribe. Thank you very much.